Okay, good morning and welcome everybody to this examination of a doctoral thesis at Mid-Sweden University. My name is Kaarlo Niskanen. I'm professor in chemical engineering and the head of the research center FSCN, and I will be acting as the chairman of today's event and your host. The author of the thesis is Hafizur Rahman, whom you can see standing with a tie on. The other main person today is the opponent, and I would like to welcome adjunct professor Emeritus Göran Bengtsson from Karlstad University. Göran has a PhD from Chalmers on chemimechanical pulping of birchwood, and he's done his career in different R&D positions at AkzoNobel, Rottneros, and the last 25 years before his retirement at Stora Enso, where he was, among other things, had the position as the manager for Stora Enso's group research program. In parallel with this industrial role, Göran has been an active lecturer and adjunct professor at Karlstad University and a member of boards and steering committees of several large R&D programs in Sweden. We are very grateful that Göran, Professor Bengtsson, that you have accepted to act as the external reviewer of Hafizur's doctoral thesis. Then we have the examination committee, where we have Professor Emeritus Germgård, also from Karlstad University, whom you can see sitting in his office. We have Professor Ralf Menk from the Research Institute Elettra Synchrotron in Trieste, Italy. There. And we have Professor Juha Fiskari from Mid-Sweden University sitting there. Welcome all you, and thank you also to you that you have taken the role to act in the examination committee. Hafizur's thesis is entitled Aspects of Optimizing Pulp Fiber Properties for Tissue and Packaging Materials. The thesis, the research in the thesis has been performed at the Department of Natural Sciences and the Research Center FSCN at Mid-Sweden University. During the first 2 years, Hafizur was working at SCA's R&D center here in Sundsvall through our industrial graduate school, FORIC. And after that, he moved over to MIUN and continued his work towards the doctoral degree. The purpose of the thesis is to improve competitive advantages for forest-based products and materials in comparison to fossil-based materials and products. The essential thing in this thesis has been to increase knowledge about the selectivity in impregnation, cooking, and refining operations of a pulp. The main supervisor of the thesis has been Professor Armando Cordova, and of MIUN, sitting there, smiling a little bit, and Professor Per Engstrand, with the MIUN background, and then Assistant Professor Börje Norlin, who is also with us somewhere today, even though I don't see him. And all of them are from MIUN. Then, of course, there's been collaboration with many other researchers, both MIUN and outside in academia and in industry. And this collaboration has been vital for Hafizur's PhD work. And especially, I want to mention the role of SCA, of course, but there's also been several other companies. Okay, what happens now is that first Hafizur will give an overview of his thesis, then we'll have a short coffee break, maybe 10 minutes. And after that, Professor Bengtsson will pose questions and make comments and remarks about Hafizur's thesis, and then we'll move on to the examination committee. And after that, everybody else in the audience has the chance to pose questions to Hafizur. And then I want to say that before we begin, Kristin Grafström is heading the crew on site to direct this Zoom session, and she'll be following, together with Richard, she's following the chat. So if you have any questions, please send a message to her, Kristin. Okay, now I will give the word to Hafizur, and I heard that you had detected one small misprint that you maybe want to mention before you start with your overview. Please, Hafizur.
Microphone.
Yes. Good morning, everyone. Thank you for my presentation, and thanks to Karlstad introduction, very good introduction. Today I'm going to I will very much say about my aspect of my pulp fiber properties for different packaging materials topic. First, I would like to mention that I have small corrections. I mean, the page number X, the page number 50 in Roman, I put it in SSD and OD just together in the separate. Neutral sulfide semi-chemical and also separately oxidative. I think everyone listen clearly. Okay. Today, there is a demand to replace the plastics from the world. So what's the demand? Now, it should be some kind of paper-based material. It is renewable, recyclable, and biodegradable. Even in the market, the people expect that all the things need to be compared, right? So the demand towards those multiple, they took the most of the responsibility to fill up the gap plastic. And then we see the manufacture of kraft pulp and CTMP is significantly increased for the production of hygiene papers, such as tissue papers, and also most of the packaging materials, for example, paperboard and liner. But the challenge in front of the industry, when they try to fill up the gap, they have a lot of difficulties. I will say the word challenge, because bleached softwood kraft pulp is the highest single cost. It was more than 50% manufacturing cost. And even for the tissue applications, dewatering and dryness is very important, and there is a very much cost here. And for example, if you look at the CTMP, whereas the production of cost of refining, cheap pretreatment, and also steam recovery, all are very costly. However, if we try to find out the questions, what we have to do now? The pulp, I was employed in the R&D, so I know how to sort it out. So they try to do that, how to develop the process to improve the key product properties, and how to improve the pulp efficiency with regard to yield and energy, and how to increase the sustainability in the process. So to doing this, what we need now, we need to understand and improve the fundamental understanding the fiber properties, and also create a significant product value and opportunities for new cost-efficient wood biorefinery systems. So on that side, we optimize the pulp fiber properties for what is for tissue and packaging materials. So we divided the three based on my research. Number one, what we need, increase the knowledge of selectivity of cooking process or chemimechanical process by optimizing, I will say, the impregnation, cooking, and refining. Our goal is to achieve and even fiber separation as possible. On the other hand, we need to improve the impregnation uniformity, because our goal is to achieve as even a degree of sulfonation as possible at the level of individual fibers. If, for example, the CTMP, we should improve the sulfide ion distribution within the wood chips before they are preheated prior to entering the refiner. At the same time, as we're thinking for sustainable process, we can integrate a part, might be in the delignification process or in some other way, to develop catalytic lignin selective coating. The purpose was to dissolve lignin as extracted as fine chemicals, for example, for vanillin production. However, the project was collaborating multidisciplinary research, but based on two different platforms. During my first almost 3 years, I worked as an industrial PhD student, SCR&D, and our Forest Research Industrial College, FORI. And of course, we collaborated Rice Economy and Karlstad University. And the later, more than 1.5 years, we collaborated with Sweden University 2 research platform, Fiber Science Communication Network, mainly Natural Science and Chemical Engineering Department, and also Electronics Department, Tensile Index communicated that research platform. And we have some kind of company shelter, Valmet and Billerud Korsnäs. So the purpose was we have to optimize pulp fiber properties for better tissue and packaging materials. So the research focus was 3 different ways. A, we looked over impregnation improvement by selective. Here our purpose was the high quality fiber. It could be for tissue applications. And here our outcome was less refining, lower energy cost. And that is mostly discussed in the paper 1 and 2. And it's presented many international conferences. And the part B, we have looked about the uniformity of impregnation at fiber level. And we try to develop a miniaturized EDXRF method and to study sulfonation at microscale level. And that methodology we have in paper 3. And lately we have integration part, improve selectivity with catalytic cooking system, and that we look for production of sustainable fine chemicals. Here we looked at only the production of vanillin, and that is paper 4. However, I can start with A, B, and in sequence. First, impregnation improve my selective. During start my PhD work, I work at the SCR&D, and we started with 1 liter digester. We took the 100 gram of drywood chips, and it was mainly from the SC Engstrand, where it's 70% spruce and 30% pine. And we took the effective alkali, almost 20%, and sulfide was 35%. Liquid wood ratio was 4:1. And we maintained that impregnation temperature between 70 to 160 degrees Celsius to get a specific copper 35 plus minus 2 and addition 40. We have developed 3 different pulps. One was the reference, and 1% wood chips for sodium bromohydrate reduced pulp, and also polysulfide treated kraft pulp. That was 2% polysulfide treated. However, we look about the only single bleaching state with the chlorine dioxide that was supplied from more research. And we also look about the fiber properties. And that's why we have targeted lower grams, 20 grams, and also 60 grams. But our PFI regulation is 0 to 2000, 500, 1000, 2000. Of course, we look up some of the fiber properties that's based on tensile index, weight zero span, Z strength, charge analysis, porosity, and water retention value. This work was passed for the fiber properties. At the end, we also looked at these dewatering properties for tissue applications, and that we only consider 20 grams hand sheet. And that's the dual time was managed 6 difference, 0 to 20 milliseconds. And that was done at the Karlstad University collaboration. So if I start impregnation improvement by selective, I divided here 3 different steps. 1 was the modification kraft pulp, 2 is the characterize the fiber properties, and finally study of dewatering properties. So I can start with modification of kraft pulp. If you look at the pictures, the green color is the sodium bromohydrate treated pulp, blue was the polysulfide, and red was the reference kraft pulp. The main difference is the charge, 2% polysulfide and 1% sodium bromohydrate. But the yield is improvement, 48.1% to 50.2 and 50.2 and the 52.6% for sodium borohydrate. I mean here, main thing, here is the main thing that this yield improvement was almost 2 to 4%. So if we go to the carbohydrate analysis, then we might get another answer. Look at this curve. The graph. We see, compare the reference polysulfide sodium borohydrate rate pulp, the total hemicellulose was increased for the sodium borohydrate. But in literature study, we know higher hemicellulose, especially glucomannan, increase the hydroxide concentrations that increase the alkali charge, but decrease the silent amount of silent. So in our case, it's look the same 2 to 4% yield improvement based on the glucomannan, and also the opposite, the silent. So it makes sense that sodium borohydrate and polysulfide has some kind of activations during this process, and that's help to yield improvement, especially the hemicellulose. If we go back to a little bit in chemical structure, so it's not my task to detail study and discussion here, but I can focus. Sodium borohydrate was a very good reducing agent, and this was reduce the carbonyl N group in the hemicellulose to stable hydroxyl N group. Actually, it prevent endwise the depolymerization of the glucomannan. So that's why stabilized against the peeling. So that was studied a lot from during 1965 to till now. On the other hand, polysulfide that we use the elemental sulfur, that is we presented as the PS. And stabilizer reactions, what we see, indole from the reducing N group, and which is equilibrium with the corresponding open aldehyde form, is believed to be oxidized to diketones structure and transferred via benzoic acid and reference to the aldonic acid. I mean, polysulfide is oxidized the aldehyde N groups to alkali stable aldonic acid. But we have a message. Reduced N group such an alcohol is more stable towards the peeling than oxidized N group. And this is studied so many literatures before. So that was the insight. And we see the higher yield for sodium borohydrate polysulfide compared with the reference due to hemicellulose yield increase. So now, the second stage was characterized the fiber properties. That I said that we have 20 gram and 60 gram as hand sheet for different PFI reflections. Also, we looked at the tensile index, fiber strength, fiber joint strength, charge, porosity, and water retention value. So I will start it with the tensile index. It's a very important parameter in my research. Just check, observe this graph. It was very nice. Look at the blue one, sodium borohydrate, yellow one, polysulfide, red one, reference. So we have 4 different refineries, PFI regulations. But if you look, the tensile index increase, especially lower refinery. This is very nice graph. It's from 39.5 to 45.5, and then it's almost 52 kilonewton per kg. I mean, we have corresponding 15 to 32% tensile index improvement for sodium borohydrate, I mean, higher hemicellulose yield pulp corresponding to polysulfide and compare with the reference graph pulp. That can be present in a better way so that you can see more interesting. Look at this curve. It's a green and red. One is the green was the sodium borohydrate, red is the polysulfide. That have been described here as a percentage increase in tensile index compared with the reference graph pulp. So it's a very interesting thing is that when you increase the refining, so the compare with the sodium borohydrate, with the polysulfide, sodium borohydrate is a higher tensile index, but it's a more interesting when it's a lower refining stage. It says that lower refining stage, I mean, for example, 500, sodium borohydrate is a higher percentage in tensile increase in tensile index compared to the polysulfide. I mean, it's have been made with the comparing reference graph pulp. So it's for the 20 grams handsheet. So that's why we have also interested where is so many fibers. I mean, the fiber index is higher. What about the 60 gram handsheet? Is the same trend that we see on the 20 grams handsheet. But only the difference is that compared the percentage increase in tensile index for 20 grams is more than compared to the 60 grams. And if we increase the refining level, then the difference is very less, but it's more pronounced when we go for the lower refining stage. So it makes sense that lower refining refining level, either sodium borohydride or the polysulfide, the hemicellulose yield pulp has a better tensile index compared with the reference kraft pulp. So we can say this message, why 20 gram handsheet is better tensile index. It might be there are fewer fibers in the fiber networks, that the joint distance between the fibers is more important for the 20 grams handsheet than in the 60 grams handsheet. So then it's also important, fiber distance properties. And that's the only good parameter weight zero spam that we did. The red one is the reference, blue, polysulfide, green, sodium borohydride. It looks like the opposite on the tensile index, that's things we see. I mean, it say that almost 8% difference from the reference, sodium borohydride, the fiber distance properties. Means reference pulp is, I mean, higher distance pulp. But compared with the, tensile index, I mean, other things, we can example the joint distance, sodium borohydride polysulfide is better pulp. That I come to the next slide. But you can the masses, what the things? It means lower weight gyrosperm sheath contain fewer fibers per gram of since pulp contains more hemicellulose. And gyrosperm value may be related with the cellulose content that we calculated cellulose yield per gram. If we see the fiber joint strength, that we do the Z strength, the curves looks like exactly like a tensile index that we did. We follow the 60 grams handsheet because it's very hard to manage for joint distance with 20 grams handsheet because the curve was almost the same. So we follow the 60 grams. So what the message is here? It looks the same. The sodium borohydride and polysulfide have a very, lower refining. We see the joint distance is higher compared to the reference. So it looks like it's a correlations between increase the Z strength, increase in tensile index for sodium borohydride and polysulfide. That could be due to increase the fiber joint strength. So the tensile index will increase due to joint strength that we can say in the modified kraft pulp. So of course, then we need to check the charge analysis because we know fiber joint distance surface charge of the fibers due to increasing in surface swelling. But in our surface charge, we did not see so much differences. Then the questions, why? But total charges, we can say, is quite okay. So when you try to study our results and also literatures, I can come to that conclusion. Increase in hemicellulose in the fiber wall, it increasing the total charge. Increase hemicellulose in the fiber wall and increase the, I will say the counteract aggregation of cellulose during the drying of the fiber. And a less aggregated fiber wall is more flexible and which can lead to increase the fiber joint strength. Then we need to check on the porosity that we did with the rice bioeconomy. Because earlier study shows that there is a relationship between swelling behavior and hemicellulose content in the kraft pulp. And also the swelling is water is strongly related to the porosity of the fiber wall. So it's happened in our case. If you look at this one, sodium borohydride is higher pore volume and compared with the polysulfide and the reference pulp. So can we say these things after all this work indicated increase the degree of swelling of the fibers in our high yield pulp, for example, high cellulose, sodium borohydride and polysulfide, increase the flexibility of the fibers, lead to increase the bond strength. And that's why you got the resulting higher tensile index of these three different pulps, especially sodium borohydride, polysulfide compared with the reference. So that's why it was needed study of dewatering properties because we know hemicellulose affect a succession of dewatering. The increase in yield could result in reducing the dewatering ability because the high ability of hemicellulose to hold the water. But it can be alternative. The increasing yield could result in increasing in dewatering ability because high yield a sheet of equal weight of fewer fibers and more open network with lower ability to hold the water. That described more in the paper too. So now the challenge two, which one we will agree. So that's why we investigated effect of refining on different dwell time that I earlier mentioned. We have a 6 different dwell time. If you look at these 3 graphs, it's very hard to follow here, but I can say what is that. If you see that different dwell time is solid content here percent and 3 different crop bulb, and from the top to down is refining level increase. It means when you increase the refining level, the degree of solid content is decreased, but it happened in all cases. Starting moment where that was not in follow the dwell time, it's just 1% solid content increase, but the rest of this follow 15 to 25% between. But that here is not, you will get clear message, but at least you get the message that solid content decrease when you increase the refining. But it's more pronounced, more effective if I explain this graph. Compare the unrefined and refined. I have followed the 2000. You see, here is almost 2 to 4% lower. I will say solid content lower compared with this dwell time on the unrefined crop pulps. So it means unrefined crop pulp has a better solid content and compared with the refined crop pulp. So we should check on the water retention value. So look at this one. This one is, blue one is sodium borohydride, yellow is a polysulfide and a reference. It means that our solid sodium borohydride pulp followed by the polysulfide had solid content increased when water retention value was decreased, but it was opposite when increase the water retention value, and then you will see the decrease. It decreased the solid content. So it means, and also it is increasing refining. I mean, it's a 0. I mean, unbeaten 500, 1000, 2000. So that's why I say the large hemicellulose content results in greater swelling of the high yield pulps. And it can be related to the hemicellulose to hold water to more open fiber network. This is the one of the important curve, I will say, because you remember this curve I said 15 to 32% was tensile index improvement, for example, 500 PFI revelation. What happened, the same thing if we compare with the solid content. I took the 10 millisecond dwell time. It's not a math factor here because it's in all cases, all the dwell time was the same. So I put the example of 10 millisecond dwell time. So if you look at the solid content, compare the tensile index here, this one was an unbeaten 500. This one, the 1000, this is the 2000 PFI revelations. It looks like sodium borohydride compared with the polysulfide and the reference, we have almost 23%, but it's a better solid content as a lower refining stage. It means hemicellulose rich pulp clearly better dewatering. I mean, higher dryness at a given tensile strength. And also either sodium borohydride and polysulfide addition can give, higher strength for a given amount of refining and also same strength with less refining. Can I conclude after these 3 different parts, crop pulp, fiber properties, and also dewatering study? The positive influence of the increased yield, where the fewer fibers and more open sheet structure dominate over the negative influence of higher hemicellulose content of dewatering properties, especially at lower refining energy level. That could very good message for tissue applications. So that was our outcome. Okay. Now is different chapters. The uniformity of impregnation at fiber level. The impregnation uniformity is important for subsequent operations, but there are a lack of measurement methods combining a spatial resolution with reasonable sample preparation and measurement time. There is no easy way to measure sulfur sodium distributions in a microscale level. If there were, it could better understanding a sulfonation prior to diffusion, possibly allow it to make more even and selective, especially I will say in the case of wood chip impregnations for manufacturing of CTMP, NSC, sulfide semi-chemical part that I said. So we need to go to a little bit background. Why we wanna go for sulfonation study? Because the efficiency of impregnation is very crucial. And also the impregnation, extended impregnation time for kraft pulp, whatever we did have. And cheap treatment technique is, I mean, it's a very complicated sometimes, utilizing the combination of steaming with compression, screw treatment, elevate temperature, sometimes later modify the chipping, maximize the force, so many things. So the basic strategy here to obtain well-separated fibers at minimum possible SIP content linked to maximize the wood softening prior to defibrillations in the chief refiner. So the challenge, because we have a kraft pulp or the CTMP, in both cases we use the sodium sulfide, sodium hydroxide, sodium sulfide for CTMP and sodium hydroxide. But the challenge is that due to overly robust and complicated methods, the degree of unevenness, I mean the degree of sulfonations, the softening is fiber prefabricated in the chief refiner is generally unknown in a microscale level. So in order to homogeneize the fiber properties, we need to study distribution of sulfur and sodium in the wood chip and individual fibers. So they improve the information uniformity to measure the low level of sulfur sodium to down to fiber level. If we go for the kraft pulp, we can follow the Engstrand principle, where he mentions we need to equalize hydroxide concentration, sulfide into sulfide concentration, low sodium concentration, and low boiling temperatures. And that might help to measure the level of sulfur sodium. And that's the concept we can use in our case when we develop the micro X-ray technology. So we developed this new methodology for pulp impurity for sulfonation study in microscale level. Today, I will not go through in details in all this step because we already presented in this thesis, this two-part, feasibility and development. This is the methodology paper based on the paper 3, and we measurement set up with geometrical, shielding, filtering, how to, it takes a long time to fill these things. And then we have a simulations and also important pinhole for the resolution setup. And then we have a development instance sample target. Generally, we took the paper sheet at beginning, but our target to take the pulp sample. We have some standardized with the salt in salt. The rest of the validations, that's an ongoing work. It will be in some synchrotron base, and that we supposed to in September. And then we have a plan for the pilot setup for pulp industry, especially in valve made and bilirubin coarseness related. That's the ongoing work. So before starting, it's good to know for the general audience, what's the XRF? X-ray fluorescence is the emission of characteristics of secondary X-rays from a material that has been excited, being bombarded with high energy X-rays. So it might eject one more electrons from one atom to another, and electrons from higher orbital fall into the lower orbital and to fill in the hole in the gap. I mean, if it's a K shell, L shell, M shell, so if electron is moving, then it's try to fill up the gap. And energy is falling, energy is released in the form of photon. So the material emits the radiations. And then we has energy characteristics of the atoms. Then we see different elemental mapping. So that's the basic things. So we developed this setup. This is the schematic. We see that this is the one of the box that we make a titanium. It's a handmade everything. And also we have covered the titanium shield box and we put the helium gas in chamber. I can come up with the white helium gas. And we have the X-ray source, the MTEX source, and then we have this, our X-ray fluorescemeter. And that is a detector. And we also connect with this inside the sample. It could be paper sample, it should be pulp sample, it could be wood chips as well. But in case we started with the normal handsheet. And we have a step motor that is 2D, so it can move X-Y directions. Of course, it's connected with the resolved spectrum with the computer systems, the PC and a multi-channel analyzer. So try to explain how work inside. And if you see this, this is the X-ray source, and this is the spectrometer, and then how it's work. First, X-ray source hit on the paper sample, and then the paper sample moving X, Y directions, is that I say. But it's not so fast that I'm saying, but it's the principle. And then it's the radiations, and we get this mapping. So the simple looks is very simple, but it's not simple that here, but this is the main process. So before starting, it was very important, a simulation model. We have MCNP simulation model, Monte Carlo n particle base, where we, if you look at this graph, we have the blue one is the air vacuum, and the red one is the helium, and the black one was the air. So our simulation said that air is not good at all because the 2 centimeter thickness of air totally absorbed the sodium, like as sodium is a light element, and also absorbed 50% of sulfur. So resulting lower signal XRF setup. So it's better for use the vacuum and helium. Vacuum is better for larger setup because it's possible to handle, but if you the laboratory scale is helium gas. The transmission image confirm that has been plotted by XOF system, the 2 centimeter air and helium comparing, helium was a better trans intensity. So in our setup, we have checked with helium gas. In our setup, we also check the salt in salt. The question is why salt in salt instead of paper sample? Because we need to see the setup is validated to see the sodium. And if we take the, for example, paper sample, for example, kraft pulp, we will not see the sodium because already the paper sample that we made is already washed by the water. So we lose sodium, everything, I will say. So that's why we look at salt in salt, where is the higher concentration with the sodium chloride. I mean, 50 gram out of 100 gram. And there are also other light elements, potassium chloride, magnesium sulfur, many other things. So we try to take the salt in salt to see the sodium at least fast, that our setup say the sodium is present. And it looks compared with the helium gas and you know, just a second. Sodium has 1.04 keV. When we energy only the 8 keV fluorescence energy that we use, and that we see the sodium image compared with helium, air environment. And also we have a sulfur. So these one say that validate the setup. That's why you use the salt in salt. So it looks like the setup is working. Then we also check the kraft pulp. We have also investigated some of the pulp as well, but here we presented the kraft pulp. And we know there is no possible to see the sodium because the sample has not possible containing sodium. The reason sodium peak was not resolved because it's a small irradiated area and low beam intensity, although we use the 8 keV fluorescent energy. These were the considerable for the sodium to further check for the high beam intensity, for example, synchrotron. And of course, it needs helium gas. It's better to use the vacuum, but in our setup, vacuum is not possible. So that's why we're looking for the pilot setup. But we see the very good sulfur compared with this here. It's better for the helium gas. So that's the setup validations. And so what we have the masses. We have a microscope project, and with these things, XRF setup that we have done, everything with the handmade. And we have a different pinhole we use for the resolution maintaining 10 to 50, different pinhole. Actually, the thing we use, if we go for only the XRF, that is 400 micrometer. But if we use, that's why you need to collimate it with different pinhole, 10, 50, different pinhole setup to make a good resolution of the special light elements. The XRF setup, that need to be now, we are working on the validation at Synchrotron. For example, we have been offered in the Phoenix, Switzerland, and there we can scan 2.5 micrometer square area, any paper sample within a few minutes. Think about that. Before sulfonation study, a lot of chemical analysis, handling, many process, is so many methods before we try. But so these we can make is something is very faster and well, low exciting energy 0.4 to 8 keV. And of course, and that's very good that you can imagine for sodium 1.0 keV and also sulfur 2.3 keV, you can, some other light elements also, you can do that. So we can put on that then. When you be happy, then we can contact with the industrial setup for some validation. Because we know that we can help the sulfonaceous affect the SIP content at least. I can give the one example. the potential reduce the electricity of production of CTMP, for example, around 200 kilowatt BDT in the recent. That corresponding to electron saving potential will be 200 gigawatts per electricity. So just think about if we have 1 millimetric ton CTMP, how the energy will be saved. So that was our findings, this process. So now the last one, improve selectivity and catalytic cooking system. Because we know during this process and the pulping, we have so much lignin. And lignin is a highly complex biopolymer material that is one of the most abundant, sustainable raw material in the world, Earth. So we investigated a catalytic lignin selective cooking method in which large portion of the lignin was obtained as vanillin. We intend to investigate this, whether we can optimize this approach further to achieve high selective cooking process, largely lignin-free fibers, and keeping the cellulose largely intact and hemicellulose still present on the fiber wall. The goal was to produce vanillin here directly from the wood, but there is a potential to produce an interesting pulp fiber simultaneously. Although this process, we only focus the vanillin, but this was the aim. Of course, it's needed. The chip type should be as give best impregnation for this process. So chip study also very important to manage this, the integration part, select cooking. So we have a target of a lot of lignin monomers, but we looked only this one. 4-hydroxy-3-methoxybenzaldehyde was the target lignin monomer, to vanillin. Can you go back to why we look at the vanillin? If you go back a little bit, background vanillin. Vanillin is one of the most important in food, by perfumery, and also by pharmaceutical industries. Now, global demand is 20,000 tons per year. And we expect it to grow more 7% in 2023. And synthetic vanillin that's based on the petroleum, it produces 85% from the glycol synthesized. And this price is around $50 to $1,000 per kg. The price depends ups and down based on the crude oil. Whereas the natural vanillin, it started from the vanilla beans, this price is higher, $2,000 to $4,000 per kg. But whereas we have a 50 million tons of technical lignin in the world, we produce pulp paper industry everywhere. So what we're doing these things, we can use these things as also vanillin productions. Because if we go back a little bit, analyze the point of market, what we see, 20% produced from lignin from here for the vanillin. And because with the low yield, we have a cost of lignin, so many issues. Ultimately, it makes it expensive on the market. Whereas the crude price ups and down, there is a commercial, but they produce high yield and also cost, they ultimately make it cheap. More than 80% of global capacity chemical produced in the lignin, 90% extracted lignin from the crop pulp. So we can integrate the process, not only for the energy purpose. 85% goes for the lignin, goes for the energy purpose. But we can also saving potential at the site. Also, we can use these things as a production of vanillin as integrated in the system. So this is very familiar for pulp industry. Look at this side. We have a wood and sawdust using for pellet and also the energy purpose. We have oxygen delignification. Why you choose the oxygen delignification? Because the purpose is multiphase and the chemical reaction during pulp production, which is that we have a better cooking process, not extending the cooking, less bleaching chemicals, and we will say the higher brightness, lower SIP content. So it's to better pulp properties, we use oxygen. So we can integrate this process inside here to selectivity to increase, to production of the vanillin. Our aim is to start from the sawdust because we also focus, but next our target to use the wood chips. I will not to say these things again because we already say oxygen delignification reduce the lignin 30 to 5%, also reduce kappa 8 to 10. But the main thing is that if you look the temperature and pressures, we use the oxygen delignification 80 to 120 degrees and pressure 6 to 8 bars and pH value better 10, more than 10. So that's the concept. So can we integrate the same way, integrated the part to produce the vanillin? That could be sustainable work. So today I'm gonna only focus alkalinity, oxygen pressure, autoclave time, and temperature. That's all. That was a setup. That's the same 1 liter digester that I use in the SCR&D. It was staying inside the Teflon. And we have an oxygen gas cylinder, 5 to 12 bar, same like a delignification process that generally do. And we maintain the temperature 100 to 130 degrees Celsius. We have a glycobath that made by Sons defibrillator, 1985 for the SCR&D. I mean, the reason that is named as a Valmet company. We have a exactly like black liquor. I mean, it's soda, so it's almost soluble. Then we have, after the acidification, is a filtration orange color that contains the vanillin. When I do this lab in the lab, our lab was full of vanillin smell. So you already know before the analysis that we are producing the vanillin. So this experimental work almost patented for the Armando groups. So I'm not going to discuss what the autoclave process, but we say that we have wood sample sawdust, 7 to 14 hours we have autoclave time, maintain temperature 100, 130. We have a crude brown mixtures and extracted with the ethyl acetate, and also that we maintain the pH 2 and take only 10 milliliter solutions, and the brown solid precipitated that washed by water, ethyl acetate, and dried under vacuum to get the vanillin. So this is my last results. So if you see this, we have a soft wood 1, 2, 3, 4, 5, 6, 7, and hardwood and crop lignin. We have the alkalinity 2 to 4, and we have also used the catalytic copper in soft 4 and also crop lignin. We have the temperatures only 7 and 14, and temperatures and also pressure 10, 5, and 12. So the interesting part, this one. If you look at these things, the soft tube 2 and soft tube 5, where is the pressure was 10, compared with the soft tube 6 and soft tube 7, where the pressure was 5 and 12, the better yield was 3 to 4% increase, only the pressure 10. But hardwood is not so effective for to get the vanillin. It might be in literature said hexanuric acid presence, but in here we see the better yield for the vanillin yield. So if we compare with only the, I will say, alkalinity increase, I mean, look at this, 2 to 4, at least 1% vanillin yield improvement. But it doesn't matter for the high yield part. Although it's a 4 molar, I mean, sodium hydroxide. But if you increase the temperatures, for example, here, 100 to 130, it jump up. Only 30 degrees Celsius temperature jump up, almost 6%. So, but the timing, 7 to 14 does not so much. I mean, we can save energy instead of not use the 14 hours. 7 hours is okay. You see, if you see this only 7 hours compared with the, you see, up to 4 and 5, it's not so much difference in the yield, only 1%. We also use the crop lignin, but that did not show very well. So it's better to use our sawdust and wood chips to get a better vanillin yield. So the conclusion is that if we have a modified crop pulp today, we have a better hemicellular rich pulps, and that increases the higher tensile index and also the higher pore volume indicated the degree of swelling, and also we have say that increased yield of the negative effect of higher hemicellular pulp. That's a good for dewatering properties for tissue applications. That's the main output in our research. And we also did improve the impregnation uniformity by XRF method. There's a new sulfonation study in the pulp industry, and that newly studied sulfonation, we do the microscale level. For large setup, we propose vacuum, and technology can be validated in the synchrotron. And the last one, our new integration method improves selectivity by catalytic approach, both oxygen pressure, alkalinity, improve the vanillin yield, increase temperatures suitable for the specific degradation of lignin, but it maintain pH and oxygen gas pressures. Soft tube is preferable for this process. And also, sawdust can be possible to use a new source of vanillin productions. So that's the message. What we're gonna do in future work. In selective cooking, dewater is not enough to say it's working for dewatering. We need to more wet pressing. We also need to fiber network study that I'm doing right now. It's not part in the thesis, I put it. We see the lower density paper, how it's work for the fiber network with E. So this method. this network behavior. So it's very important. I'm working with Professor Tesuik at this Wiseka. And also we need to create behavior. It's very important. And we can also go for modification, gyroglucan and CMC. And also important to check on the retention time and the digester. That was not observed during my part, but it also needs to be future. And uniformity in impregnations, we can use the polycapillary actives instead of the different pinhole, 10, 15, because that is the efficiency increase 150 times. If we compare with the 10 micrometer, 10 micropin pinhole that we use in our sample, and that was handmade. And of course, can be used an online setup also. Synchrotron validations is needed, and we can use the different wood chips. And if we cut in the microtome 60 to 80 micrometer thick layer and continue the work. And catalytic approach, of course, we need a real industrial wood chips, investigate a larger style, and also fiber properties if we use the wood chips. Our main target, enhance the research, upgrade industrial technology. That's all. So the next challenge is nothing is impossible. To get the proper funding, research collaborations that I'm doing the last over the 5 years, continue to work for industrial setup. This is the very important slide. I have been supervised so many academic people, especially thanks to recent my licentiate to continue my PhD work, Professor Armando Cordova. He is a very high knowledgeable and very nice organized person to give the straight directions to do it. So it's no matter when he called me, he can call anytime. So I know he can call anytime. So I really thanks to him. Professor Engstrand, he's an amazing person in my life. He was started my PhD as a main supervisor and continued the supporting my end of the work. He showed me the scientific world, how to do the research proposal, how to do collaboration, how to do this. So I was lucky as a PhD student of him that he showed me the world, how to do that. I'm very happy. Thank you so much, Par. Börje Norlin, he's also a very nice person, very easygoing. That's why it's happened that I collaborate with us to the electronics department to work with his group. I have a supervisor with the Mikael Lindström at the beginning and the professor who was from the KTAs, started my research work. Especially thank Peter Sandstrom, R&D specialist who worked with me as a shadow for every day in my research work during SC-R&D. He's very professional to do that. Thanks, Peter. I think he's in my online today. I also collaborate Professor Lena Salman, Rice Bioeconomy, Professor Tetsu Isaka, who was working in the Mitsui fiber networking. And he always said, I never choose the topics that was not has future. So when he chose my topics to work with me, then I feel it's really workable. Professor Lars Nilsson, Karlstad University and his group, thank you so much. And all these things in beginning connect with the Forest Research Knowledge Foundation was acknowledged so much, but the rest of the work connect with the E2CMP, EcoMet, and also sustainable packaging material that is connected with the European Regional Fund, Sundsvall Community and Campaign Foundation. Thanks to this funding, Professor Bengtsson, Armando Cordova, and also Dr. Gunilla Peterson. Others company I like to thanks that SCF, Valmet, Billerud, Koshnas, Palpa, all are working with connecting in this. If we continue with this, my knowledge, family, friends, it will be huge 1 hour. But especially thanks to my wife, my little 2 kids, Anabia and Alvira. They give a lot of patience. I promise I'll not write second PhD thesis. My family, my father, my mother, I will be emotional. My father was my morning sun in my last 5 years. Every day I started with work to talk to my father. He knows my all the research work. He knows, he gave me the power, energy, just like a motivated. You can do that, you can do that. Although he's not my background, but he's very professional to that. My mother impression, my relatives, brother, sister, everyone was shadow. Colleagues, oh, this is very big. I can't say all the things. Thanks everyone, because of my colleagues, especially in the last, Steven, Faisal, Luca, all are working together. Thank you so much. And especially thanks my department health Dan, and before Eric heads the chemical engineering, they did a good job. Thank you so much. Thanks for listening.
Thank you, Hafizur. Really exciting, energetic, interesting presentation. Well done. Now we will take a short coffee break, 10 minutes. We will continue 11:05. with Professor Göran Bengtsson's questions and comments and so on. So see you soon, everybody.